In this video, I'm looking at structural, condensed, and skeletal formulae of organic compounds, the different ways of showing the structure of a molecule. To begin, functional groups, the classification of organic compounds. How does the classification of organic molecules help us to predict their properties? Well, the term organic originates from organisms. For many years, it was believed that organic chemicals could only be obtained from organisms. The range of organic molecules is infinite. For this reason, organic molecules have to be grouped into families, most commonly homologous series, so that the properties of a range of molecules could be understood and predicted based on the behavior of functional groups, which are common to all members of the grouping or homologous series. As far as the formulae are concerned, and that's what this video is really concerned with, organic compounds may be shown by different types of formula. I've got empirical and molecular. I've got structural, full and condensed structural formulae, stereochemical and skeletal. Firstly, empirical formula, the simplest ratio of moles of atoms of each element in a compound. Molecular formula, the actual number of moles of atoms of each element in a molecule. And I've got an entirely separate video on empirical and molecular formulae. Structural formula, also known as displayed formula, shows all of the atoms and the bonds between them. Structures are clear and there's no ambiguity. The full structural formula shows all atoms and bonds. For butane 1-ol, butane tells me 4 carbons. Ol tells me OH. Butane 1-ol tells me the OH is on carbon number 1. I'm counting from the end. Structural formulae enable us to see the arrangement of atoms within a molecule. They are most useful when considering how chemical reactions happen. Condensed structural formula groups atoms together but still shows the order of atoms in the molecule. Here I've got my 1-bromobutane again, bonds not shown. Or I could represent it as CH3 and then CH2 twice with CH2OH at the end. Skeletal structural formula or graphical formula abbreviates by using zigzag lines instead of carbon atoms and ignoring the hydrogen atoms. We know they're there anyway. These are simpler to draw and use, particularly with more complicated molecules. So if I look at the ends of each line, 1 on the left, 2 having gone up, 3 down, 4 up again, that's 4 carbons with an OH on the end, butane 1-ol. Stereochemical formulae are usually reserved for showing the three-dimensional arrangement of atoms in a molecule. Wedges. By a wedge, I mean the one drawn in dark blue to a hydrogen bottom left. Wedges show an atom or group is coming out of the page towards us. Dashed lines show an atom or group is going into the paper. Stereochemical formulae are usually reserved for showing the three-dimensional arrangement of atoms in a molecule. Very important in stereochemistry, and I will be doing an entirely new video on that. So, full structural formulae must show all the atoms and bonds in a molecule. For pentane 1-ol, 5 carbons, OH on carbon 1 at the end, all bonds shown. Condensed structural formulae should be on one line, that's a big point, with carbon atoms in order to show what is bonded to each carbon atom. I wouldn't be wrong to say CH3, CH2 in parenthesis 3 times, CH2OH. My skeletal formula uses the zigzags to show the carbon atoms. Omit the hydrogen atoms. Again, we know they're there, but include the functional groups. From the bottom, that's 1, to the top, that's 2, bottom 3, top 4, bottom 5, and then the OH, penton 1-ol. For structural formulae, I'm seeing one on the left in the middle. This is of methyl propane. I find it more useful to look at CH3, CH, parenthesis CH3, and CH3 again. Parentheses show what we call a side chain. Looking at my full structural formula enables us to see what we mean by a side chain. It's a carbon branching off away from the main chain. And for my skeletal formula, 3 carbons in line and 1 extra line showing the side chain. Bute 1 ene, bute 4 carbons. Ene means a double bond. I see it there. Bute 1 ene means the double bond is at the end. I can represent this with CH3, CH2, CH, CH2, my condensed structural formula. Just to say, substances with a double or triple bond are unsaturated, and in my skeletal formula, I've shown the double bond as 2 lines. Finally, being in group 14, carbon atoms always gain 4 electrons when they bond. This is almost always means forming 4 covalent bonds. Carbon is unique in that atoms of carbon can join to each other any number of times. They can catenate. Catenation simply means identical atoms bonding covalently to each other any number of times. There's no limit to the number of carbon atoms that can join together in a chain. There may be single, double, or triple bonds between the carbon atoms at parts of the chain, on top of which carbon atoms can also form rings. In the little diagram below, I have cyclo, meaning ring, cyclohex, meaning 6 carbons, cyclohexane, all bonds are single, which means every carbon there has 2 hydrogens. Cyclopentane, just the same. Cyclo, a ring, pent, 5 carbons now, ane, all single bonds. If you got anything out of that, please hit like and please subscribe for more content.